Good morning. So there's a lot of words in that title, so I'm just going to dive in. And we're going to start talking about machine learning. So machine learning is an area of computer science and data science that uses specific algorithms that learn from data and allow computers to find connections in data without the need for them to be explicitly programmed. This is a very fundamental shift in how computers were programmed previously and how we think about data. Clearly, I don't have enough time to go into a crash course on machine learning, but basically a typical machine learning neural network would look like a series of inputs, some computational nodes called the hidden layer, and then the results of those nodes are mapped to some outputs. When we talk about deep machine learning, it's the same sort of inputs and outputs, but the computational nodes there's a lot more of them, and their interconnection is highly complex and layered. Machine learning isn't anything new, and there's lots of applications for it that are being used right now. If you've used your cell phone this morning, you've probably interacted with a machine learning system at some point. However, there's been a big advance in the technology in the last few years where major companies like Google, IBM, Microsoft, Amazon.com, and even Facebook have been investing large amounts of resources into the technology. And what that's resulted in is a number of new systems that are either low cost or open source that make the technology very, very available, where once it used to be sort of a very esoteric and specialized skill, we now have a lot of really powerful tools at our disposal. In addition, we now have really robust libraries that can be accessed through generally accessible and well-known programming tools. So let's look at an example of how we might use machine learning in psi research. So I've been working on a project that visualizes FieldREG data. And when we talk about FieldREG data, typically we start with a group of people who are engaged in some sort of common event or task. We set up a random event generator in the background, we collect some data, and then we analyze that data to look for deviations in randomness. In the project I'm doing, we start with a group of people, but we ask them to focus on a very specific intention or idea. We then run a reg, we collect the data, but instead of looking for statistical differences, we model the data in 3D now and visualize it. There have been other projects that have visualized 3D or reg data in the past, so this is just sort of my take on it. And when we do this process, what we end up is with images that look like this. This image was created from data that was collected during Julie Beichel's talk at the Vail Symposium in Vail, Colorado, where participants were asked to focus on the idea of their community. This was one where a series of meditators were focused on a breath meditation. This image was generated from data, excuse me, when an individual was asked to think about his depression and social anxiety issues. And the intention here was of abundance. So if you look at these images, they're all very colorful and they're all very pretty, and there's a lot of overlap between the content, but there are some interesting and striking features in them. And when you ask the people that participated in their creation, the participants will often report that they feel as if their intention is somehow reflected in the image. Now, clearly, that is a very subjective process, and I may have done nothing more than create very, very pretty Rorschach pictures. But it's an interesting idea to sort of consider. So to play with that a little bit, I ran 2 sessions in which we did 5 sessions in which the intention was love, and 5 sessions in which the intention was hate. And these are the resulting images. Now, again, a lot of overlap, a lot of similarity between these images, but there's also something kind of different between these images as well. So how do we quantifiably define the differences between these 2 data sets? Well, one way would be to use a traditional research method. We recruit participants, we analyze all the data, we do all this stuff, but we have to develop some sort of test or sorting or scoring task that may lead us to that difference eventually. However, for this particular project, it's very speculative. And this is a kind of a pretty resource-intensive process. So instead, I wanted to sort of remove the human element bias from it and started looking at deep machine image learning systems, or classifiers. And the one I came up with is a commercial system called Classify, which is available to anyone. You could use it right now if you want. It has an open API that you can use. It's free, or depending on how much data you want to use, there's a small cost to using it. And it's specifically designed for image concept and feature tagging. So what does that mean? That means if you get this picture of a bird that I took, you run it through the classifier, it returns a series of tags that identify it, including like bird and no person and nature and tree, etc. So what happens when we run our 10 images through the system? Well, excuse me. Not surprisingly, you see a lot of overlap between the tags that are returned for the two data sets, just like we would expect, because there's a lot of overlap in these images. But the really weird and interesting bit is that the classifier tagged 4 of the 5 hate images with a unique identifier. And that identifier is triangular. That's a very, very specific feature. And I can actually use that now to track the triangular feature back into the visualization software and potentially back into the data set. So what I've been able to do here, what the classifier is able to do here, is actually start giving me the groundwork for a testable hypothesis. So what did we learn from this? The software made this test possible in just a couple of hours. There was considerable time cost and savings as compared to traditional approaches, and the exploratory test demonstrated the potential value of machine learning in efficiency and potential hypothesis generation. So machine learning has a lot of potential, but it's not without its problems. And one of the sort of epic fails in machine learning has been the Google Flu Trends project, where Google decided that it could take a bunch of its search data and convert it and use it to predict flu outbreaks around the world. And as it turns out, it was very, very bad at it. And Google silently sort of killed the project after a while. Another sort of more recent fail was Microsoft's Twitter bot, which used natural language processing to teach the software to talk like a teenager, there's a lot of T's in that sentence, on Twitter. And after being online for about a day, it turned into a racist jerk. And they had to shut it down and apologized. And fortunately, they, the system did come back online for another day or so. And before they finally took it offline completely, it sent out one last very prophetic tweet, which was, "You are too fast, please take a rest," which I think is a really important message from our future robot overlords. All that being said, there's been some really interesting applications for machine learning in the sciences, and this one has made the rounds in the news. It's a controversial find, but I think it's worth noting that in just 3 days, a machine learning system was able to chug through all the published data on a particular problem and find the solution to a 100-year-old biology problem. And I think this quote is pretty interesting. This problem in our approach is nearly universal. It can be used with anything where functional data exists and the underlying mechanisms are hard to guess. So when I hear statements like that, I really begin to think about how we might be able to apply these kinds of technologies and this new set of toolkits to parapsychology. And of course, we have all these interesting sets of data available to us that may be ripe for exploration through machine learning technologies. So in summary, researchers now have access to new, powerful, low-cost, or free machine learning tools. Exploratory tests using visual FieldREG data showed the potential benefits offered by machine learning in terms of efficiency and hypothesis development. And although we need to be cautious, parapsychology may benefit from machine learning analyses of existing psi data sets. I want to thank my research partner, Dr. Julie Beischel, all the people at the Windbridge Institute that support this work, the volunteers that took place in the sessions, of course, you for attending. A quick shout out to Julia Mossbridge, who dragged me kicking and screaming into trying to look at this more empirically, and to Michael Dugan for his never-ending criticism of this project on Facebook, because, you know, Facebook is where all the real science happens these days. Thank you very much.
Thank you, Mark. One quick question for you. Was that last slide by Michael Levin at Tufts?
Last slide. This slide?
No, farther back. Yes.
Yes. Yes, it is.
Okay. Thank you.
Why would you need the intermediate step of making images? Can you not just feed the random data stream into the network and give it some condition, like this is condition A, this is condition B to learn on?
What would that condition be?
Sorry, I didn't understand.
What would that condition be?
Yeah, for example, you say this generator was made under love intention and the other under hate, and the network is supposed to learn to distinguish between these two.
That is completely possible. Yes, you could absolutely do that. But that's not what I was doing with this project. I ended up with these visualizations because I was interested to see if there was something else in the data that wasn't showing up in the statistics that the visualizations might show. So now I have this visualization data, and I'm interested to see what's in there.
I'm so excited to hear you do this talk because I've had like maybe no less than 6 conversations with people on the side about like why isn't anyone using some kind of machine learning for this stuff? And I think it's definitely the future. And secondly, just the step of constructing the images by itself I was pretty impressed with just that. But one question I had, and I know this is probably maybe you're just kind of getting your feet wet in this, but so if I understand correctly, you're using these already constructed images and then trying to look at the relevant feature and saying, okay, there's this common feature within the hate images, for example. Mm-hmm. Where I've seen this applied is in like in a predictive context. So if you have the images constructed on several individuals and maybe across multiple sessions, and then trying to extract, okay, what are the relevant features that could kind of classify love versus hate images, and then use the second half of your data set to try to predict what the intention was based on the image that was constructed for that individual, then you can start to see some really, really useful stuff, including like, hit versus miss in psi paradigms, rather than did they have a hit rate that's reached a significant threshold, or what are the relevant pattern features in like an fMRI experiment, for example, that's associated with a hit versus a miss in some remote viewing or something like that. Does that make sense?
Yeah, absolutely. Thank you.
Hi, excellent presentation.
Thanks.
Just a clarification question. Did I understand correctly that you gave the Clarify network, which was pre-trained with some other images, your images, but you didn't train the network with your images?
That is correct.
Okay.
Because it would be impractical.
Sure.
Right, because the Clarify system has been trained with every image on the internet.
I was just checking to make sure.
Yeah, absolutely.
Thank you, Mark.